folks, Dr. G here. Today we're doing a lesson on numerical integration in Python using an NMR spectrum as an example. So here is a simulated NMR spectrum that I created of ethanol, right? The one that you can drink. So that is an NMR spectrum of ethanol, and the data that was used to produce that plot is right here in this CSV file, right? So comma separated values. That's what CSV stands for. So here's all that data. So how can we take this data, load it into a Jupyter notebook and plot it? And further, besides plotting it, we want to be able to take a numerical integral of this and answer questions like, what's the total area here, right? Under all the curves. What's the area only under the quartet or the triplet, right? We want to know, we want to be able to take numerical integrals to figure out the area under curves here. So these are our two goals: to be able to produce this plot and also to be able to take numerical integrals of the entire thing or only portions of it. So before we can do anything, we need to get this data loaded into the Jupyter notebook. So let's first import the libraries we're going to need. So let's import pandas as PD. Let's import OS for operating system. Let's import matplotlib.pyplot as PLT. As PLT. So these are three very common libraries in the sciences. Pandas, operating system, and matplotlib as PLT. So we're going to import all of these in our first step here. I have a warning, there's something I have to update on a library, but it's not going to cause any problems. So we're just going to roll with that. Next, we want to tell the Jupyter notebook where it can find this data. So I'm going to call this variable data path, and we're going to find it using OS. So we're going to say OS, the operating system library, and it's kind of like a library within a library. We've got os.path. So there's all kinds of different functionality that comes with path for finding different file paths and things like that. And specifically, we're going to use a function called join. And so what the join function does is it will put together a file path for us. So all we have to do is tell it how to get there from here. And where is here? Well, it's the place where this Jupyter notebook lives. So this Jupyter notebook is called NMR Integration YouTube. There it is, it's right here. So starting from that point, if we go into the directory called data, then we find our file that we want. So the only things we need are data. So that's the name of the one directory here. So there's data. And if we go into data, we're going to have spectral data.csv. So I'll put that as the next entry here. And so that will produce a path. And so if I print this out now, data path, we see that this is what data type, right? It has quotes here. It's a string, right? So this will produce a string. Now, could I have just typed out this string and used that as my data path? Absolutely, I could have done that. But I'm on a Mac right now. If I were to share this with somebody who's on a Windows machine, this file path wouldn't work correctly. So by using OS, what it does is it creates a file path based on what the computer's operating system is. So that's why it's important to use os.path.join instead of just typing out your file paths. This makes it more portable to other machines. So, so this gives us a path to our data. And if we were to read this in now, so I'm just going to call this raw spectrum. So this is just kind of a raw data coming in. So I want to import that as a CSV. Well, the reason we brought Pandas library into the Jupyter notebook today, one of many reasons, is that it has a great function for reading a CSV file, right into a Pandas DataFrame. So I'm going to use that function. And not surprisingly, it's called read CSV. Excellent name. And so all I have to do is give it the path. So if I give it data path, then I've read that data in. And now this is a Pandas DataFrame. Pandas DataFrame is an object that has a method called head, which allows us, if you think of it as the data just kind of peeking its head out so it can take a peek, right? So that's what we did there. And if we look at this, notice how this is in bold up here, right? So what these are, this is our header. So what's a header? That's like the names of each column. So it's assuming that the first thing that was read in is the header. But this isn't true, right? We have chemical shifts and we have intensities. So what we need to do, we need to tell our Python interpreter here that there is no header. So if I do that, now we look at it, now this is included in the data as it should be. So now our data is loaded properly, but this is still not ideal because now I could refer to the first column as 0 and I could refer to the second column as 1, and that's kind of clumsy. So why don't we give our columns names? So this DataFrame object, I can access the columns, right? So the columns is an attribute of this object. And I could access that by just saying .columns. So if I do that, it tells me that my columns are 0 and 1. Again, terrible column names. But what I can do here is combine accessing the columns attribute here with the assignment operator, right? At the equal sign, a single equal sign. If I take the thing on the right, assign it to the left, then I can do that here. So I'm going to assign some more reasonable column names, and let's call them ChemicalShift. And let's call it intensity. Intensity. So if I do that, now an assignment has been made for the columns. So now if I call this again, if I access this attribute columns, now it tells me that the names are ChemicalShift and intensity. That's much better. And if I look at the head, that looks much better, right? ChemicalShift and intensity. So now let's address plotting this data. So I want to produce a plot that looks something like that. Well, the first thing to consider is, does this Pandas DataFrame have a plotting method built into it? Well, let's see what happens. If I paste that there and I just say .plot, sure enough, it does. But if we look at that and we look at that, okay, not bad. I mean, you know, we see that a plot happened, but if we notice, it's plotting ChemicalShift and intensity as two separate functions. It's basically plotting both of them as a function of the index. So what I mean by the index, like the row number, right? Row 0, 1, 2, 3, 4, right? Going all the way down. So it's plotting two functions as a function of the index. So that's not quite right? We want it to look like this. So it turns out, for this plotting function, we can assign our x and our y. So if I say x equals, and then I have to give it which column I want to be x. Well, I want ChemicalShift to be x. And then I have to specify what I want y to be. Well, I want y to be intensity. So now this is looking much better already. But comparing it to this, there are still some differences. So one key difference is this one has a legend, this one does not. So the first thing we could do is get rid of the legend. So the way to do that is to just say legend equals false. Now we don't have a legend. So that was an easy fix. Now there are two other main differences between this plot and that plot. The plot that is our target of what we're trying to make it look like, it only covers an x range going from 0 to 5. So that's different. This goes 0 to 7. So we want to leave out all that stuff past 5. So that's one issue. The other issue is that, as is typical with an NMR spectrum, it goes in descending order for the ChemicalShift value, right? We've got 5, 4, 3, 2, 1, 0. That's the normal way to do it. This is going 0, 1, 2, 3, 4, 5. So this is kind of an unusual thing to do, but we can make Python do it. And so we'll address that last. at least last for the plotting stuff. So how do we only show it from the range going from 0 to 5? Well, there's different ways to do this. One way, we could change the X limits here. There's definitely a way to do that, and that would solve it very easily. But rather than doing it that way, I want to show you how to cut a Pandas data frame. So basically, let's say you have a data frame like this and it's got more data than you want. You want to cut that down. So an example, just kind of an everyday example, if you have survey data from a bunch of people and one of the columns are the people's age, and you only want people who are older than 20 and less than 30. Can you cut that data to only select those people from the group? Absolutely, you could do that. So you could do that with the Pandas data frame, and so that's what we're going to do. So rather than plotting our raw data like this, I actually want to create another data frame that is only our plotting data. So let's create another one. Let's call it Spectrum for Plotting. Spectrum for Plotting. And again, we're going to use the assignment operator, and we're going to make a cut of this data. So we're going to do some cut to that. So right now I'm not going to execute this cell yet. Let's play around with cutting this data first. So if I add another cell here, I take the raw spectrum here, paste it there. If I want to be able to cut this data, so the simplest way to cut this data is to select only certain rows. And so I want the rows where the chemical shift is less than or equal to 5. That's my goal here. So in order to show you how to do that, first I'm going to give you the whole code, and then I'm going to break it down. So the way that's done, we go raw spectrum, square bracket, raw spectrum, and we're going to select only the chemical shift less than or equal to 5. And that's how you cut the data. So if you notice when this is outputted, it starts at 4.99999, right? This is now the highest value for chemical shift. So it did work. But I don't want you to just copy this and not think about what it's doing. So let's add another cell above that here so that we can break this down bit by bit. So let's first start with the innermost piece. So the innermost thing is this part. So what's happening here? Well, this is how we select only the chemical shift column. And you notice this is actually the way we would do it for a dictionary as well, right? If we have a dictionary where one of the keys is chemical shift and the value is a list of values like this, it would look exactly the same. So this is often why people will create a dictionary and then generate a Pandas data frame using a dictionary as input. So that's what we did here, is first we select only the chemical shift data. So here's the actual values, 7, 6.9993, etc. Right? We've got all these values for the chemical shift. Well, now if I take just this part, this less than or equal to 5, let's see what that part does on its own. So if I paste that there, we run that, we see it returns a bunch of false, true, true, false, right? So it's returning true and false values. So what this is doing is it's checking to see, do each of these values, are they less than or equal to 5? Is that true or not? And so they start out false, right? Because they start out with a value 7, and then they get smaller and smaller, and eventually it switches over to true. And if we want to check, like, what's the data type, right? What data type is being produced here? This is always a good thing, right? You always want to pay attention to what data types are your inputs and outputs for anything you do as you're writing code. So let's check the type. And it turns out this is a Pandas series. So the way I like to think of a Pandas series, it's like a Pandas data frame, but it's only one column. That's kind of how a series behaves. So what we've learned here is that if we have a Pandas series of Booleans, trues and falses, and we pass that to a data frame inside of square brackets, what this is actually doing is it's selecting the rows that are true and it's rejecting them if they're false. And so that's what we're getting here. So that's the meaning of this code here. I didn't want to just give that to you and have you not think about where it comes from. So I could delete this one again because it's just a copy of this one. At this point, we've fully built it up. And anytime you see code that you don't quite understand, it's always good to start taking it apart. Be like, all right, what does only this part do, etc. So this is a good habit to be in. So anyway, this can be our spectrum for plotting. So let me copy this, and we're going to name this as our spectrum for plotting. So if we call that spectrum for plotting, and then here where we were originally plotting our entire raw spectrum, let's swap that out. Let's make that the spectrum for plotting now. Let's put that there. Now if we plot it, check it out. It stops at 5, right? So this goes 0 to 5, this goes 0 to 5. So now to get this plot to look basically like that one, the main thing we need to figure out is how do we have it go from 5 down to 0 instead of a 0 up to 5 in terms of the chemical shift. Now, you might be thinking like, well, can I just take my data frame and reverse the direction, right? To have, just have the rows go the other way, right? From 0 going up to 5 instead of 5 down to 0. You could do that, but it actually won't change how it gets plotted. So it turns out that if we want to change the way the axis goes here, right? If we want to invert the x-axis, there is a command for that that comes with the matplotlib.pyplot library. So we imported that, and this is a big reason why we imported it, is that I knew we were going to want to do this. So we need to incorporate that now. So it turns out in the matplotlib.pyplot library, which we have imported using a nickname, right? We imported this matplotlib.pyplot as plt. So anytime we want to use this library, all we have to do is type plt. So we type plt, and then there's GCA, get current axes. So this is a function that is available to us because we imported pyplot. And so that's a function. We call that, and then from that function, we call another function called invert x-axis to invert the x-axis. And lo and behold, now it is going the opposite direction, right? Instead of 0 to 5, it's going 5 to 0. So now it's going the right direction as well. So comparing these two plots, we're going to call that good enough for our purposes here. So we wanted to be able to see what's going on in our spectrum, and we're able to do that now. So next, we're going to move on to numerical integration. And specifically, we're going to do the simplest kind of numerical integration there is. We're going to add up the area of a bunch of rectangles, right? So using a scheme kind of like this, if you have some smooth function shown in blue here, and maybe you don't know the value of that function, you don't know how to take that particular integral, you say, well, if I chop this up into a bunch of boxes, I know the area of a box, length times width, I can just add up a bunch of areas of boxes and treat that as an approximation for the integral. That's what a numerical integral is. And of course, if you're looking at, is that really the best way? No, that's typically not the best way. Often what's best is the trapezoid rule is a common way to do that if you make trapezoids instead of rectangles. But for today, we're going to use the rectangle rule because it's going to be good enough for what we want to do. And it's super straightforward to code. So I want you to see how easy it is to code numerical integration in Python for the rectangle rule. So for this particular rectangle rule, we're going to draw a box where the height of the box is the left corner of a rectangle, right? So you start at some initial point. You say, okay, start at the point x equals 0. What's the height at x equals 0? It's this, right? It looks like it's around 1. You say, okay, that's my first box, and I'm going to have a box width of, in this case, it looks like it's 0.2. So if I go 0.2 in the x direction, that's my width. Now I don't establish a new height, right? For the trapezoid rule I would, but we're not. We're doing rectangles. So we say, okay, keeping that same height, I got the height here. We'll call that 1, and the width is 0.2. So the area of this box is 0.2, 1 times 0.2, length times width. And then the next rectangle, well, that starts at 0.2. So we say, okay, what's the height of the function at 0.2? Yeah, it looks like it's about 0.9, something like that, right? We'll call that 0.9. So we'll say this height is 0.9. The width is the same, it's 0.2. So now it's 0.9 times 0.2, and that is the area of this box, and then you add that up. So you're just gonna keep doing this over and over again. And notice that the width of the box is staying constant. So you don't have to multiply length times width every time, right? If you're multiplying by the same width each time, what mathematical operation can you use? We can factor, right? We can factor out that width. So we can just add all the heights and then multiply by the width once at the end. And so that's what we're gonna do for our NMR spectrum as well. So if I wanna add up all the heights and then multiply by the width, well, first of all, I better figure out what the width is. Well, the width is changing in our x-axis, our chemical shift axis. So if we look at that, it goes from 4.9999 to 4.9992, right? So that's the jump, that's what it's doing. And so I could eyeball that and subtract it, but let's be a little more precise about it. Let's select exactly that value and subtract from it that value. And so one thing that I will tell you that you can assume is true about this data set is that this width is the same every time, right? Every step in X is exactly the same. So I can take the difference between any two consecutive chemical shift values, and that will give me the box width. So I'm going to use the iloc function. And what this iloc function does is stands for index location, I believe. So if I want to go .iloc, that allows me to select values by their index. And it goes in the order RC, row then column. So the way I always remember that is RC Cola, right? If you've ever heard of RC Cola, it's a soda. So that's how I always remember it, RC. So row then column. So if I want the first row and the first column, well, remember in Python, the counting starts at 0. So that would be 0, 0. So 0, 0 will give me the very first chemical shift value. So let's run just this to see what it is. Yeah, 7. We remember that it started at 7. Remember our original plot started at 7. That's right. So, okay, so first row, first column. So now I want to go one down. So I want to go, okay, second row, first column still, right? Because we still want chemical shift. So we'll subtract from this. We'll subtract from this the second value for the chemical shift. So second row, which is going to be index 1, but it's the same column, right? Because chemical shift is the column. So if I do that, and I take that difference, here's our value. So that is the width. This is the width to quite a few number of decimal places. So what we're going to do, we're going to set that equal, we're going to assign that to width. So width is going to be our variable that holds the width of the boxes. So I can do that. And now, if you got a data set that you had never seen before, what I would recommend you do, don't just assume that the width of the box is constant. What I would say you should do is write a for loop that loops over the chemical shift and takes the difference between every consecutive value and then plot it. Or even take the mean value of it, something like that, right? Probably plot it to see if that changes. I'm not going to do that in this video because I don't want to go too off track. But you could do that if you wanted to check that that width stays constant. And if it weren't for the fact that I'm telling you this data set, the width is constant, I would want you to do that. It would be a good practice. So we've established the width of our boxes, right? So for this, we know how wide each box is, except, applied to our function, the NMR spectrum, not this function. So great, we've established width. Now we just have to add up heights. And then once we add up the heights, then we multiply by the width once at the end, right? Just like I said, if all these boxes are width 0.2 and I want to get the area here, all I have to do is check all the heights of the boxes, add up the heights, and then multiply by 0.2 at the end. It's the same thing here. So now let's begin by integrating the entire spectrum. Let's say, what's the area under this entire curve, right? All of it. Well, if we want to add up all of these heights and then multiply by the width at the end, well, we have a data frame, right? We have a data frame that's storing all the heights and the widths, right? So our data frame, let's go back to the raw data frame because we want to use all of them, right? Our raw spectrum is that. These are all of our values. So if I want to add up all of the heights, that means I want to add up all of the what? The chemical shifts or all of the intensities? It's the intensities, right? It's the heights that I want. So if I want to select the intensities, we've seen how to do that, right? We do this, and now I've got all the intensities. So then you might say, okay, so this is a Pandas series, right? When I remove one column from a Pandas data frame, it produces data type series. So you might be wondering, okay, this series object, does that have a built-in method that can sum up all of its values? Well, let's find out. There we go. I typed SU, hit tab, and it suggested sum. So that's a function. So this is a built-in method for a series. So if I run that, it takes a sum. And so that's the sum of the heights. I want the area. So now I just have to multiply that by the width once. So if I do that, there's our width. We called it width. Good. We gave it a reasonable name. Always a good habit. And we multiply these two together. The total area under the curve is about 6. So there we go. In this one cell here, we've done numerical integration using a rectangle method. Well, now, what if I want an integral of the quartet only, right? This quartet only, I say, well, okay, great. What's the integral under only the quartet? Well, if we think back to earlier in this lesson, we learned about cutting the data. So if we want to select only the quartet here, right, we want to select the rows from the data frame where the chemical shift is less than 4, but greater than, let's call it 3.25, right? So less than 4, greater than 3.25. That should capture the quartet pretty well. Just eyeballing this, that's good enough for today's purposes. So how do I select that? Well, we did a selection earlier, so let's copy what we did earlier. And let's build off of that. So if we want to select the quartet, let's call it quartet. Quartet equals, so we have quartet equals this selection. Now, of course, this isn't the correct selection. We need to fix it. So we want chemical shift that's less than 4. So we said less than 4 and greater than 3.25. So we could just change this to a less than 4. And we also want it to be greater than 3.25. So I can put that here and say greater than 3.25. But we want both of these to be true. So we have to put an and in the middle of here. But we're not quite done. So we say we want this to be true and we want that to be true. Right? If both of these are true, then select those rows. If not, don't include them in our quartet. Right? We're creating our quartet data frame right now. In fact, we can even call it quartet DF just to remind ourselves it's a data frame. So we're creating a data frame that is a cut of our raw spectrum. Right? We're cutting the raw spectrum, only selecting the rows where the chemical shift is less than 4 and the chemical shift is greater than 3.25. So the thing we have to do to make sure that things get evaluated in the correct order is we need parentheses. So this is just order of operations, right? Like, please excuse my dear Aunt Sally, right? It's that again, right? So it's from mathematics, but basically it's applied to programming. We say that, okay, this 4 and this raw spectrum and the and, it actually won't evaluate in the order we want it to evaluate in. So we put parentheses to force Python to evaluate this first and evaluate that, then put them together with an and statement. So both of these things need to be true. The chemical shift has to be less than 4 and it has to be greater than 3.25. So now let's run this cell. Great, no errors. And to make sure we did it okay, let's just plot our quartet here. So let's copy our plotting code here. I'll copy that. In fact, let me copy the whole thing. I'll copy all of that, paste it here, but instead of spectrum for plotting, I'm going to plot quartet. So I put that there. Now we run it. And look at that. We selected the quartet pretty darn well, I think. So let's run with it, right? We've confirmed that we've really selected the quartet, right? Oh, never assume that things work the way you want them to, right? Sometimes we learn that the hard way. So always test everything. So we find that we have selected the quartet. So now let's do our integration. So we're just going to copy this. Copy that, paste it there. But instead of integrating our entire raw spectrum, we're only going to do quartet. So if I copy that, paste that there, run that, and we see that our quartet integrates to about 2, right? So this is about 6, this is about 2. So now the instructions for the rest of the assignment tell you to take some other integrals and do some other things, but I think I've given you enough to build from. I'd like you to figure out the rest of that yourselves. So hopefully you've seen how powerful this is, right? Even if this data set included a really fine grid with 1,000,000 points, our code would work the exact same way, right? We're not relying on having a smaller data set like scrolling through Excel or something like that, right? This will scale to really big data sets. This same code will work on small data sets or large data sets the same way. And that's one of the main things that makes Python so powerful for data analysis compared to other things like Excel. All right, folks, I hope you enjoyed today's lesson, and I'll see you in the next one.